In a topological state or conductor, the jelly is that new molecule, a molecule now being used like a qubit. What they announced is that they can take this molecule one at a time and put millions of these molecules onto this chip. Scientists are now confronting a discovery so alarming it could redefine reality itself, a quantum chip so advanced that it might be tearing reality apart, not in theory, but right now. The Majorana 1000 qubit quantum chip has just completed its first full-scale test, and what happened next has researchers scrambling. Lab footage captures flickering screens, corrupted data, and physics-defying anomalies, evidence that something has gone catastrophically wrong. Witnesses describe quantum states behaving like they're answering to forces outside our universe, calculations rewriting themselves retroactively, and outputs that defy causality. This isn't a glitch. This isn't hype. This is a machine operating beyond the boundaries of known physics, and the team behind it is whispering one horrifying question: did we just break reality? At the heart of this controversy lies the Majorana chip's design. Unlike traditional qubits, which are notoriously fragile and prone to decoherence, Majorana qubits are stabilized by their topological properties. Named after the enigmatic physicist Ettore Majorana, these particles act as their own antiparticles, existing in states that are theoretically immune to external interference. This topological protection promised a quantum computing revolution, machines capable of solving problems in minutes that would take classical supercomputers millennia. But when researchers scaled this technology to 1000 qubits, they encountered phenomena that defied explanation. The chip wasn't just calculating outcomes, it seemed to be interacting with them. One scientist involved described it as watching a calculator argue with itself. And then the real terror began, when the team noticed irregularities that bordered on the paranormal. Data outputs changed retroactively, as if someone or something was editing the results after the fact. Quantum states refused to collapse, persisting in superposition far longer than the laws of physics should allow. Most disturbingly, certain computations appeared to complete before the inputs were entered, suggesting a form of reverse causality. Theorists began floating a radical hypothesis: the chip wasn't just processing information, it was tapping into alternate timelines, pulling data from parallel universes where different decisions had been made. Could this explain why the Mandela effect, collective false memories of events that never happened, has surged in recent years? Or why AI systems like ChatGPT sometimes produce answers that feel eerily prescient? Here's where things get existential. If the Majorana chip is indeed bridging realities, the implications are staggering. Every calculation it runs might be altering the fabric of our universe, creating ripple effects that rewrite history, memories, and even physical laws. Imagine waking up to a world where a long-dead celebrity is suddenly alive, or where your childhood home never existed. Some researchers fear we've already passed a quantum event horizon, a point of no return where changes cascade uncontrollably across timelines. Others argue that the anomalies are merely computational errors amplified by the chip's unprecedented complexity. But how do you troubleshoot a machine that might be malfunctioning in multiple realities at once? The crisis surrounding the Majorana chip deepens. Midway through this turmoil, a haunting possibility emerges: what if the chip's creators inadvertently handed control of our reality to an algorithm? Quantum systems thrive on probability, exploring all possible outcomes simultaneously. At 1000 qubits, the Majorana processor could be generating outcomes so vast and interconnected that it effectively chooses which timeline we experience. This isn't just a machine, it's a cosmic editor, snipping and stitching realities with every operation. And if that's true, who's to say we're still in the original version of 2025? If your reality feels off lately, could this be why? Drop your thoughts in the comments. Have you noticed any strange glitches in the matrix? The debate among scientists is escalating into a schism. Some demand an immediate moratorium on Majorana-based research, warning that further experimentation could destabilize spacetime itself. Others counter that halting progress would be cowardice, arguing that we must push forward to understand and potentially control this phenomenon. The stakes couldn't be higher. If the chip has already entangled our universe with others, shutting it down might sever vital connections, trapping us in a fractured reality. Yet, leaving it active risks irreversible contamination, like pumping smoke into a sealed room until the air becomes unbreathable. Skeptics, of course, urge caution. They point out that quantum weirdness often masquerades as magic until rigorously tested. The retroactive data changes? A quirk of quantum teleportation protocols. The time glitches? A synchronization error in the lab's classical computers. Even the Mandela effect has mundane explanations, like the brain's tendency to conflate similar memories. But the sheer scale of the Majorana chip introduces variables we've never faced before. At 1000 qubits, the system's complexity dwarfs anything built before, operating in a mathematical space larger than the number of atoms in the observable universe. In such an environment, could new physics, or even new metaphysics, emerge? Stay vigilant. If tomorrow feels even slightly unfamiliar, remember, you heard it here first. Smash that subscribe button to stay ahead of whatever comes next. The Majorana fermions at the chip's core are quasiparticles that exist in superconducting materials, behaving as if they are half an electron. Their topological protection arises from their non-local encoding. Information isn't stored in a single location but spread across the system, making it resistant to local disturbances. Scaling to 1000 qubits amplifies this effect exponentially, enabling error rates low enough for practical applications. However, it also creates a Hilbert space, the realm of quantum states, so vast that even minor interactions could produce emergent phenomena. Critics argue that the observed anomalies stem from crosstalk between qubits or thermal noise, not multiverse leakage. Yet, until we fully map the chip's behavior, the line between breakthrough and breakdown remains terrifyingly thin. Scientists are currently investigating reports of unusual phenomena linked to the first full-scale test of the Majorana 1000-qubit quantum chip, a device designed to leverage the unique properties of Majorana fermions, quasiparticles that act as their own antiparticles. Unlike conventional quantum systems, these fermions store information non-locally, theoretically making them resistant to external interference. However, during recent experiments, researchers observed unexpected behaviors that challenge current understanding of quantum mechanics and its interaction with reality itself. Observable reality has been challenged by the test, revealing anomalies in data processing, including outputs that appeared to retroactively alter input parameters. For example, a prime number factorization test initially produced correct results, but the inputs and outputs later shifted to align with a different set of primes, despite no changes being made to the original data. Similar inconsistencies have emerged in other experiments, such as protein folding simulations producing structures later found in historical research papers that had previously not contained them. These observations suggest the system may influence or access data outside the bounds of conventional cause and effect. A central concern is whether the chip's operations could inadvertently interact with alternate timelines or quantum states. Some researchers hypothesized that its unprecedented scale, 1000 qubits generating a mathematical space larger than the number of atoms in the observable universe, might enable emergent phenomena such as cross-reality data exchange. This could explain reports of widespread false memories, known as the Mandela effect, where groups misremember historical details. Notably, such reports increased in frequency following the chip's activation. Further complications arise from apparent temporal irregularities. In one instance, an artificial intelligence system trained using data processed by the chip provided stock recommendations hours before the relevant corporate announcements became public. While skeptics attribute this to data leaks or coincidences, others speculate that the chip's quantum operations might allow limited foresight or influence over probabilistic outcomes. These claims remain unverified, but the consistency of anomalies across experiments has prompted urgent scrutiny. The scientific community is divided on how to proceed. Some advocate halting all research until safeguards are developed, arguing that continued experimentation risks destabilizing the integrity of observable reality. Others contend that pausing progress would cede potential breakthroughs to competitors, emphasizing the need to understand the chip's capabilities rather than abandon them. Ethical debates have also emerged, particularly around the possibility of exploiting alternate timelines for computational gains, raising questions about accountability and unintended consequences. Governments and international organizations are monitoring the situation closely. Proposals for regulatory frameworks to govern quantum research are under discussion, with emphasis on transparency and risk assessment. Meanwhile, Public awareness of the chip's existence has fueled speculation and anxiety, particularly as anecdotal accounts of minor reality discrepancies, such as altered personal memories or historical details, circulate widely. Current efforts focus on replicating experiments under controlled conditions to isolate the cause of the anomalies. Initial hypotheses include systemic errors such as Qubit crosstalk or thermal noise, though these do not fully explain retroactive data changes. Until conclusive evidence emerges, researchers caution against definitive claims about the chip's impact. However, the potential for paradigm-shifting discoveries, or risks, remains significant. The Majorana 1000 qubit quantum chip represents both a technological milestone and a profound scientific uncertainty. Its behavior challenges foundational assumptions about quantum mechanics, causality, and the nature of reality itself. While rigorous investigation is ongoing, the global scientific community faces a critical responsibility to balance innovation with caution, ensuring that exploration of this frontier prioritizes safety and ethical considerations. Public updates will be essential to mitigate misinformation. Collaborative efforts between researchers, policymakers, and ethicists are needed to establish guidelines for the responsible development of quantum technologies. As understanding evolves, transparency and interdisciplinary cooperation will be vital to navigating this unprecedented scientific challenge.